I told one of my colleagues, hey, let us actually run the test bed for 11 days non-stop. And we will collect the data. This data is now in 102 countries.
Amazing.
And more than 20,000 downloads.
Yeah.
By more than 82 faculty members across the world and so on.
Welcome to another session of the CRPO Vodcast. Today, we are taking a closer look at one of the most critical and under-discussed challenges in cybersecurity today: protecting operational technology in essential services like water, energy, and public utility. Our guest today is Professor Aditya P. Mathur, Founding Director of iTrust. iTrust, a research center at the Singapore University of Technology and Design, has been quietly building technologies designed specifically for real-world OT. So welcome to the show, Professor Aditya.
Thank you very much, CK.
The work happening at iTrust reminds us that good research only matters if it makes it out into the real world. So when it comes to critical infrastructure, that couldn't be more important. The systems that keep our water clean, our lights on, and our cities functioning. These aren't glamorous targets, but they're so important for us and critical for us to protect. Can you maybe start by saying or telling us what was the background behind the motivation to start iTrust and what was it actually meant to do?
Thank you, CW.
Yeah.
So let me give you a quick history first of iTrust. So it was in 2012 when SUTD was launched in collaboration with MIT. I was invited by then Professor Tao Chong to manage iTrust. And I must point out that there are many people who helped set up iTrust or initiate iTrust. But the name that is always on my mind is that of the then Chief Defense Scientist, Professor Kwek Tong Boon. I still remember vividly the letter that he wrote to SUTD saying that MINDEF will support a center named iTrust for research in cybersecurity. So that's how it started. And then the question, of course, was if iTrust is to be a center for cybersecurity, what should be its focus? And so that was a question that I had in my mind. And I looked around, and at that time, it was 2012, there were already many centers in the world that were focusing on cybersecurity. And including Singapore, NUS, NTU, they all had some sort of cybersecurity research going on. So I told myself that there's no point in doing the same thing that others are doing in Singapore and the rest of the world. So what should I be doing? And interestingly, I came across a paper from Berkeley, which was on critical infrastructure, water security. And that really opened my eyes. And that gave me the basic idea iTrust should be focusing. I decided and I discussed with MINDEF that we will focus on critical infrastructure.
So tell us more. Tell us more about iTrust.
So at that time when we started, the question was, okay, so critical infrastructure. So what do we do in critical infrastructure? I don't remember why I thought water is the one that we will start with. But we start with water. And then I was wondering, well, if we do research in critical infrastructure, say water, then what should be the nature of this research? The traditional way in which many faculty members in many universities in the world do research is that they sort of have ideas, and then they sort of have graduate students who they play around with those ideas and write papers and so on. So I thought if it is a critical infrastructure, then it has to be different from how research is normally done in many universities. I'm not saying everywhere, but in many universities. So I talked to, there were some really good guys in MINDEF. Chai Wang, for example, was one guy I remember very well. And I talked to them. I said, look, we need to create an actual test bed. I mean, I was very fortunate. They agreed. Then, of course, the question was the money for the test bed and all that, but all that worked out eventually. And that's how our first test bed for water treatment plant, the SWAT, which is quite well known in the world, came about. Gave a contract to a designer, and then we gave contract to Flowtech, and eventually here it was, SWAT. Now one of probably the world's most famous water test bed in a university.
Maybe from the point of being a pioneer in this area, right? And then looking at what has been achieved over the last 10, 15 years. Um, at a point in time when you conceived this idea, did you actually know that you're going to walk this journey and create what we have today? Or is it one in which the ideas are always emerging depending on what you have achieved, and then more collaborators came in, you got new ideas? Because what I'm trying to do is then trying to also um, raise the awareness in terms of the research community that when they start something, they not necessarily be so hung up about what's at the end, but rather just following the next step and your hunch to create what is the new.
So I cannot say all the ideas and the tools that we have now were in my mind at that time. But one thing was definitely on my mind, that whatever we produce, we must actually take it to the actual plant. I said, Guy, let's actually look at the design of the plant. And then based on the design, let us create detectors that will be useful for the plant engineers who are first responders. So that was the original idea. And our first paper was around that time, which is the most cited paper today. At that time, I was also very interested in making sure that what iTrust does not remain only in iTrust. It should go to the whole world. So I told one of my colleagues, hey, let us actually run the test bed for 11 days non-stop. And we will collect the data. And in between, during those 11 days, we will also launch attacks on the test bed. And we generated data. And we made this data public.
Oh, thank you so much.
Believe it or not, CW, this data is now in 102 countries.
Yeah, amazing.
And more than 20,000 downloads.
Yeah.
By more than 82, faculty members across the world, and so on.
What was your motivation, or what was your thought or your thinking in terms of persuading them, making them believe in you? I think we saw one aspect, which is your determination to want to share this with the world. So in the end, it's really about thinking about benefiting the whole entire world and to see the benefits translated, right?
First of all, a physical test bed is, if you show something on a physical test bed as opposed to a twin or a simulation, it is more likely to be impressive, and people will say, yes, this is working on a real system. So that was one thing. The other thing was, the twin does not change. The twin remains the twin as it is when you designed it, but the plant changes. The plant degrades. And that becomes a major challenge. In fact, right now, today, when we are working with PUV, that is a challenge we have to focus on as time progresses. That the plant, whether it is PUV plant or whatever plant, their components are degrading. And that has an impact on our technology, the false positives and things like that.
I think this idea of the test bed may be unfamiliar for a lot of our audience. Could you just describe the test bed in a bit more detail, in particular the part about the adversarial attack on these water plants, how the test bed actually allows researchers to study the vulnerabilities, and more importantly, I think the users or the audience will also want to know what kind of impact can such adversarial actions actually cause on the water plants.
Okay, so the first test bed that we built, SWAT, Secure Water Treatment Plant, it is a 6-stage water treatment plant. So the water comes in into stage 1, then it goes to chemical dosing, then it goes to ultrafiltration, and then it goes to UV, ultraviolet dechlorination, then reverse osmosis, and then the backwash. So this is a very typical architecture for drinking water plants, not wastewater, drinking water plants. And so that's what our SWOT is. Now, because we have this test bed, and it's a very modern test bed, what I mean is that it has SCADA, PLCs, and all the technology which you'll find in real plants. Because of that, we are able to simulate cyber attacks on this plant. How do researchers study the impact of attacks and how good our technologies are to avoid the damage and things like that? So that is a big advantage of having a physical test bed. You can actually design and launch attacks on the test bed, look at the impact, and then see how the impact can be mitigated through your technology.
So in a typical water plant, I mean, of course, you've seen many of them. How many sensors are there typically in the water plant?
So there could be about, I'll not talk about the exact number of sensors. Our test bed, SWOT, has just about 50 of these.
But various types of sensors.
Yeah, various types. Yeah. Our test bed has just 50. But a full, let's say, 16 million gallon per day plant, a wastewater plant, would have a few thousand of them. So you see what we are dealing with. We are dealing with a research which is being done in a much smaller plant, maybe 100 times smaller than the real plant. And this research has to be now transported to a real plant. That is the challenge we face.
So from a attacker's perspective, I mean, given all these sensors, actually, what would be the pathways to actually, attack the sensors? Would it one be where they can do it remotely, or they have to be physically within the plant to do so?
Yes, so there are several pathways. Of course, uh, the worst case scenario is that there's a insider
Mhm.
who has access to the entire plant and can do whatever he or she wants. Okay, that's the worst case scenario. When I say insider, insider does not necessarily mean being physically inside the plant. So take, for example, the Christmas attack on the Ukraine power plant through another country. In that case, the attacker was sitting in that country, not in Ukraine. And that person was able to get access to the SCADA of the plant and then was able to open a circuit breaker that led to several thousand people losing power. So this is one pathway to launch attack. Another pathway is, of course, you can, if you're an outsider and somehow your plant is connected to the internet, maybe not directly to the internet, but through business logic. So there's a business logic for the plant, which actually says how much water was produced today, how much was actually consumed, what is the billing. So that business system is sometimes connected to the actual SCADA, which should not be done actually, but sometimes people do it. Yes. So this was an attack last year in 2025, 2024, I think, or 2025 January,
Yeah.
where an attacker got hold of a plant in Texas, and they caused the water to flow out from a large storage tank from where the water actually goes to customers. So the water was just falling, and people who were walking by, they were saying, why is this tank overflowing? And interestingly, the attackers actually posted a complete video of that attack.
Thank you, Prof, for explaining about the test base, attack pathways and all this. So, but there's this question, all right? The technologies of the past to protect the water plant versus what you are deploying now in Atlanta and working with TUB and Enzyme. Can you describe the differences and the evolution of these technologies over time and why you see the need to develop anomaly detection using AI and so forth, Yeah.
The technologies that have already existed for a long time are essentially what we call as IT-centric technologies. So in any plant or any organization today, there are computers that are communicating with each other, and this communication is done at what we call as the IT layer. What we decided was, as I said earlier, we decided that the IT level technology is helpful in detecting intrusions into the system through IT. But when the intrusion actually happens, and if it is detective, it takes quite some time for the time the entry happens, intrusion happens, and the time it is detected. Between this time from the entry to the detection, the damage might have already been done. In addition to what is already existing, can we do something at the OT level? That means at the plant level where you have the actual sensors and the pumps, etc., so that the plant engineer gets to know immediately, even before the IT guys have detected your intrusion.
People think that with the antivirus being installed, the firewall, you'll be safe. But it turns out that this takes an extraordinary amount of time sometimes to detect and to even do the forensics, etc. So at this point in time, in between these two periods, you really see the damages happening in the water plant. So, Professor, I on that note, I also like to ask you, and thanks for sharing about having the need to instrument all these various aspects of the OT plant or the water plant. A big thing today, of course, is artificial intelligence, and I think yourself, you invented some methods and systems in order to detect this even more accurately. Can you explain a little bit about all these technologies that you invented and deployed?
Yes. So we started, as I said earlier, we started with pure design-based detection, and we did not use any AI there, no machine learning, pure design-based. We can actually create a model of different variables, continuous variables in the plant, and then use these models to make predictions, and then compare these predictions with the sensor values, and then see if the predicted value is quite far from the sensor measurement.
Yeah. So, Prof, just now you mentioned, um, of course, now we really know, right, the fundamental ideas behind the test base, etc., the attack pathways. Could you touch on a little bit more about the actual cases that are happening in the world?
From Australia.
Mm.
It's a very famous attack called the Maruchi sewage water plant attack. I believe that is probably the first cyber attack on a water treatment plant. I don't remember the exact year, but it's at least a decade old.
Okay.
So what happened was one of the employees was fired,
Mm-hmm. Oh.
and that employee went out, and unfortunately, the IT folks did not remove his account, so the account was still valid.
Mm-hmm.
So he went out and he logged into the system, and there was a pipe through which the sewage would flow if a valve was opened. So he went into the system, opened that valve. The result was that huge amount of sewage flew into a public park. So what happens is whenever you change the state of a component in the plant, for example, if you change the state of a valve, that state change is not allowed at all times. There are only certain times when that state change is allowed.
Mm-hmm.
PLCs have that logic inbuilt into them. But if you spoof something, then that logic fails because the PLC simply says, this is what the sensor value I'm getting. There's a command going into this valve to open it. But is this valve to be opened in the current situation? And that is the technology we have, which we call as plant protection. So this technology is actually looking directly at the sensor data, not the data that is going to the PLC, which could be spoofed. So this plant protection is a new technology that we have developed.
So let's cycle back maybe a little bit about the anomaly detection and AI grid. I understand that that is being implemented with Ensign and then on PUB, and that's actually the of course the CRPO grant that you have won. So congratulations again. Um, Going forward, I'm sure you discover a lot more insights for which you to build new technologies. You already mentioned one. And of course, I think we can look forward to the success of this deployment, right?
Yes. So this deployment that we want to do in PUB is a major challenge for us. I think one of the things we are uh, investigating is how do we scale up the DAD and AI grants, and that's why we have this project from CRPO, which is essentially to investigate how these two technologies can be scaled up. So we are partnered with Ensign, and Ensign has developed a very nice tool that creates AI kit and DAD for a plant automatically.
Yeah.
We have not yet tested it in PUB.
Mm-hmm.
Okay, so over the next year we will test it in PUB, and then if you talk to me after about a year or so, then I'll be able to tell you what was the outcome of that test. And I'm really hoping, because this is a dream project for me.
Yeah.
All these years, we were never able to get permission from any plant to go in and test out these technology, deploy these technology. It was very difficult to get that permission. Now, fortunately, with the help of CSA, PUB, and you guys, CRPO, we have received that permission. So we have that permission from PUB for one plant, and we also have the permission from another plant in United States. And the result of this deployment is going to be, I think, very interesting for future translation, deployment of these technologies and commercialization of these technologies.
So just now I was mentioning about the grant that Professor Wong, and this is called the CRPO Translation and Innovation Grant. So in each of this funding, actually there's a requirement for the principal investigator like Professor Aditya to be collaborating with a industry partner. And so the whole idea is that we can translate the research that is being done by the institutions into something that is productizable and commercializable. So maybe, Prof, can you talk about the relationship between yourself, SUTD, iTrust, and versus Ensign as collaborator?
SUTD, as you know, is a university. iTrust is a research center inside SUTD. So SUTD hosts us. And the grant that we got from CRPO and also previously from CSA, that grant has helped us create a partnership with Ensign. So Ensign, those of you who don't know, Ensign is a cybersecurity company in Singapore, and they do a lot of research and mainly development and deployment of cybersecurity solutions within Singapore's landscape. The partnership is actually, I would say, a three-way partnership. So iTrust has developed the technologies. AI Crit is and DAD. These are technologies for detecting anomalies or undesirable behavior in a plant. Access to these technologies has been provided to Ensign to develop a system that will automatically generate AI Crit and DAD for any plant. So that's where Ensign comes in. But then the question is, which plant are we going to use for assessing the effectiveness of these technologies? And that's how PUB comes in. So PUB has agreed for us, iTrust and Ensign, to work together on one of their plants. These technologies have to be tested for their effectiveness in some plant. And we are very fortunate that PUB agreed to allow us access to data and also the design details of one of their plants.
Could you explain the part where what Ensign is doing in terms of the generation of
Yes, DAD is a pure design-based detector, anomaly detector. AI Crit is a design and machine learning-based detector. So far, when we developed these detectors, everything was done manually on SWOT. So because SWOT is a small plant, we were able to do it successfully. So these two technologies perform very well on SWOT. But now, when you have to take these technologies to a plant like the one at PUB, manual generation of these detectors is just not possible. So that's where Ensign came in. So Ensign said, okay, we will use artificial intelligence to take the data from the plant. So we take that data, and that data goes into the Ensign's OT's analytics solution, and
what is
outcomes
what's
AI Crit and DAD.
in a very simple term, what is this output? There are rules, there are
So,
models.
Yes. So there are two things that come out.
Yeah.
As far as DAD is concerned, rules come out.
Okay.
As far as AI Crit is concerned,
Okay.
models come out.
Okay.
So these models come out, they have been trained.
Yeah.
And so these are the trained models, and then the rules are inside that. But having said that, it sounds pretty exciting, right?
Yes.
But there are challenges.
Of course they are.
There are a lot of challenges. So, for example, the number of rules that is generated is huge.
Just to give a rough, sense, how many rules are we talking about actually?
Okay.
1,000, 10,000, I don't know.
Okay. So for SWOT, which has only 50 sensors and actuators, 550 rules.
Okay.
Just for SWOT. So it will be many thousands of rules that will be generated for that plant.
Okay.
So we have to now think about, first of all, how to reduce the number of rules. And we have some ways of doing that. Okay. and then making sure that these rules that are generated are really will not generate false positives.
Yeah.
That scalability challenge has not yet it's still there.
Okay. So we maybe talk a little bit more about the DAD and AI crate. Realistically, if you're going to do this for other plants, right? What is the real impact that DAD and AI crate can really deliver?
Yeah, it's a very good question. So uh, imagine there's a plant operator sitting in the control room. The plant already has a lot of alarms, but the alarms that we generate using AI Crate and DAD are beyond the standard alarms which you will find in almost any plant. Because when the plant is designed, the designers introduce these alarms at the design time. But what is not there, and we hope in the future it will be there, but right now it is not there, are alarms which are based on correlations across components, like valve and sensor, flow sensor. So now, when assuming that all the challenges that I mentioned earlier are overcome, and these technologies are actually deployed uh, and running in real time, then these DAD or AI crit will generate an alarm whenever there's an anomaly that is not generating an alarm otherwise.
So, in other words, with the baseline sensors and the alerts, we have one level of intelligence to suss out issues with the plant, right?
Yeah.
Actually, with DAD and AI Crate, you are adding a new level of intelligence. The more that you do this with the data that's coming in, depending on all the situations that you just mentioned, actually allows the detection to be more adaptive.
Yes.
All right, to the situations and so forth. I think that's something that really makes sense because today one of the biggest challenges, or rather blind spot, if you will, is that people typically just deploys machine learning models without the rules portion. So in this aspect, DAD and AI Crit actually is very special because it actually balances both. Because there's no way that the AI will know everything. Neither is it the case that the anomaly detection will know everything. So by combining these two concepts together, it actually makes sense to bring the intelligence to the next level.
Yes.
In your own experience, right? Uh, with the rest of the countries, of course, US being one of them. How do you compare Singapore's organization uh, in terms of critical infrastructure protection, cybersecurity, versus, say, for example, in the US?
I think the only thing I'll say about US is it's too big.
Mhm.
It's too big. There are, I don't know, 180,000 or something like that water plants and all that. So I think I really cannot talk much about what they are doing. But I must say something about Singapore. So I can tell you that from 2012 onwards, when iTrust was set up,
Mhm.
Singapore has never let down on grants and support for OT research. Second thing, if you look at the critical infrastructure in Singapore, I know about water quite well. Even though it is very difficult to get into PUB to deploy your technology, that part I understand why they want to do that. But what they do is excellent. They protect their plants in a variety of ways. For example, the drinking water that they send out, they have fish that they use to check whether this water, if that special fish survives, then that means this water is good to drink, in addition to many other parameters. So they have a large number of technical solutions and also uh, physical parameters, all the way from government down to the actual implementation plans. Singapore is probably one of the most effective countries in the world in implementing cybersecurity in critical infrastructure. The R&D landscape of Singapore is something for which the Singapore citizen should be proud of. If you look at the not just OT research, but look at quantum research, quantum computing, and so on. It seemed to me they understand the international landscape, where the problems are and where should Singapore focus on research. I think they do a good job of understanding, and then
translate.
transforming that understanding
Yeah.
to actual policies and these research projects and so on.
What kind of research will you foresee iTrust embarking on?
Since 2012, the work we have done is using traditional methods of research, all manual. So the question now in my mind, and I've discussed it with my colleagues, that the new world order is different already. AI is clearly disruptive technology. And iTrust should not be moving forward with the same ways of doing things. So, what is the new way of doing things? So, for example, iTrust could create its own agents for complete design of a secure critical infrastructure, whether it is power or water and so on. So, you do the complete design that is secure automatically, as much automatically as possible, and only the implementation, the actual building, has to be physical, of course. So this is one challenge that iTrust can take over. But you won't believe the amount of effort we have put in creating these digital twins. We don't have to do the same thing again. So the whole question now, as we move forward, is how do we make use of disruptive technology for the betterment or for the improvement of the design of secured and critical infrastructure? That is the major question we have in front of us now.
Okay, thank you for the sharing. I think the future is about one in which we will leverage all these technologies to make, the critical infrastructure safer.
Absolutely. And somebody told me that Singapore is investing a huge amount of money in AI. And I think iTrust and SCTD and the other plans will benefit from that. We are ready to move forward in this new world.
Professor, thank you so much for all your sharing. Thanks for telling us about the background to iTrust and how it have come so long in a way to where PAD and AI create is. And I wish you the very success in the deployment of PUB and then also the future for which you just described. So thank you very much, Professor.
Thank you, Mr. Sirus. Thank you.
Thank you. If you have enjoyed watching the content today, follow us on CRPO, on LinkedIn and YouTube. And thank you so much for tuning in.